Hello everyone, this is a lecture on the chapter Dual Nature of Radiation and Matter. This is chapter number 11 of class 12. So, of course, you demanded a revision class, okay? So, this is particularly that. I won't be going that elaborate with the topics. So, firstly, we saw what is a photon, right? So, photon is particle of light basically. So, we also call it as a packet or bundle of energy, okay? So energy of a photon is given by the relation E equal to h nu, which is hc by lambda. So here nu is the frequency of the photon, lambda is the wavelength of the photon. Okay, c is the speed of light, h is the Planck constant. All right. So this is for one photon. Okay, for n photons, the relation becomes E equals to nh nu. Okay, so which can also be written as nhc by lambda. Okay. Now we see some properties of photon. Number 1, photon travels with the speed of light, right, in vacuum, which is 3 into 10 to the power 8 meter per second. Now this C relation can also be written as frequency into wavelength. Number 2, photon do not possess any charge. Now photon is chargeless, therefore it is not affected by E and B fields. What are E and B fields? These are like electric and magnetic fields. That is number 2. Number 3, point number 3, photons possess momentum. The momentum relation is P equals to E by C. Now E is hc by lambda, right, and C was already there, so after cancellation you get h by lambda. So you can write down P equals to E by C equals to h by lambda. So this is the momentum relation, momentum for a photon. Number 4, photons of a particular frequency will have same energy and momentum. Okay, for we can write down same energy and momentum for photons with same frequency. Number 5, rest mass of a photon is 0. Okay, rest mass is 0. Now rest mass 0 indicates that photon is never at rest. You will never find a photon at rest. Okay, therefore you call it as rest mass of a photon is 0. But it does have relativistic mass. Now, what is relativistic mass? Mass due to motion. Relativistic mass. So mass due to motion, the relativistic mass of photon is determined by the relation m equals to E by c square, which is h nu by c square. Okay, this is equation number 5 in accordance with the PDF. So we'll calculate energy of a photon in electron volt. Energy of a photon in electron volt. So E equals to, we had hc by lambda. So the value for h is 6.63 into 10 to the power minus 34. C value is 3 into 10 to the power 8 divided by lambda. This value will be in joule, okay, SI unit. This gives you 19.8 into 10 to the power minus 26 divided by lambda joule. This relation is to be remembered as this is the SI value. Now when you convert this into electron volt, what do you have to do? 19.8 into 10 to the power minus 26. You'll divide by the value of E, that is 1.6 into 10 to the power minus 19 lambda. Now this has been converted into electron volt. The calculated value will come out to be 1243 or 1237. Okay, you'll see, you will cross verify the calculation. I'll be writing down the rounded value, that is 1240 into 10 to the power minus 9 divided by lambda electron volt. Now why we round up this value like 1240? Why do we write it as 1243 as 1240? The reason being convenience of calculation while dealing with this number, okay, in comparison to 1243. And similarly, we have something called work function. We'll see it in a while. What is work function? The relation for work function in electron volt can also be written as 1240 into 10 to the power minus 9 divided by lambda naught electron volt. Okay, this will also remember. Now we have the definition of work function. Work function. The work function is basically the threshold energy with which electrons are held in a metal plate. Okay, so if you want to knock these electrons out from this metal plate, the incident light should have energy which is greater than this work function. It should have energy E greater than work function. Okay, so it's a value, or it's a measure of the minimum energy the incident light should have to knock these electrons outside this metal plate. So the relation for work function is phi naught equals to h nu naught, which can be written as hc by lambda naught. Now nu naught is like threshold frequency, lambda naught is threshold wavelength. Okay, now in the PDF you'll find some values for different metals are given: potassium, sodium, cesium, etc. Just look into the values once, you need not remember them. Next we have threshold frequency. Threshold frequency is this, basically this nu naught thing. This is threshold frequency. It is the minimum frequency, it is a measure of the minimum frequency the incident light should have to cause photoelectric effect. Okay, again, threshold wavelength is the maximum wavelength an incident light can have to cause photoelectric effect. Alright, now so what is photoelectric effect? Photoelectric effect, what is it? Now it is the phenomena of causing or of knocking out electrons from a metal plate with the incidence of high energy light or high frequency light, you can say. Okay, so with this what will happen, let me show the radiations as this. Okay, so the result will be electrons are knocked out. Electrons are knocked out. Now you have to remember, this is there in the law also, that photoelectric effect is a one-to-one effect. One photon is capable of knocking out only one electron, not two electrons. Therefore, if there are five photons hitting the metal plate, 5 electrons will be knocked out. Okay, so this is what you call as photoelectric effect. Now for photoelectric effect to happen, incident light energy should be greater than phi naught, that is in terms of energy. Incident light frequency should be greater than threshold frequency, that is nu naught. But incident light wavelength should be less than the threshold wavelength. Okay, so it's like one condition is valid, then all the three conditions are valid. Okay, because these relations are also coming out from the first relation only. Now experimental arrangement. So for this I'll just copy the diagram. So you see here, this light is causing photoelectric emission from this metal plate. Okay, it is high energy light is striking the metal surface, electrons are coming out. Now this is a cathode, this is the anode. Now anode is electron deficient, cathode is electron sufficient. Now whenever you do not connect a battery even, you see that electrons which come out, they are collected by the anode, because this is already electron deficient. Okay, now if you apply positive charges here, what will happen? The same electrons will be accelerated, they'll run faster, because positive will attract the electrons. Now you have one more situation where you make this negative. Now, when you make them negative, they start repelling the electrons. Okay, or you can say the negative potential does negative work on the electron, that is a repulsion work. The resultant effect is electrons are getting retarded now. Therefore you call this as retarding potential, you call this as accelerating potential. Okay, so for a certain value of retarding potential, it could be -5, it could be -7, we'll see it later. Okay, so for a certain value of retarding potential, none of the electron reaches the collector plate. So that is a condition when this emitter connected measures zero electric current. Okay, now the work done by this particular potential when there was no current in the emitter, okay, is W equals to VQ we know, right? So here the potential for which no electron reaches here, you call that as cutoff potential. You denote that with V naught. Okay, and since this potential is doing work on the electrons, therefore in place of this Q we write down E, and therefore the work done becomes EV naught. Okay, so this is equal to, now no current reaches here, it means that this work done is equal to kinetic energy or maximum kinetic energy of these approaching electrons. Therefore you write down EV naught equals to K max. Now this K max is the maximum kinetic energy of these electrons. Okay, so when this maximum kinetic energy is balanced by this negative work, then only electrons do not reach this collector plate. Otherwise, if the electrons has more kinetic energy, like if there is a greater than sign here, then of course you won't have V naught here, you will have EV. Okay, under that situation electrons are reaching the collector plate. Okay, I hope this is clear. Sorry. Therefore you can write down EV naught equals to K max. In place of K max you can write down half MV maximum square. Okay, now you might ask, like, why this maximum thing here? Because some electrons can have zero energy also. Okay, now whenever you have a metal plate, the electrons which are on the surface as compared to the little bit inner ones, they will be knocked out more easily. Now when they are knocked out more easily, they have more available energy for their kinetic energy, for their motion. Okay, so this is one important relation, we'll be using it ahead. Next you have Einstein's photoelectric effect. Now according to Einstein, the total energy that is incident on a metal plate is used in two manners. A part of this energy is used to overcome the work function, the remaining part is used to deliver or give kinetic energy to the ejected photoelectrons. So this is the relation, Einstein's relation. You have to remember only one relation, but we can derive other relations from this. Now energy of incident light, you can, while solving numericals, you'll find this energy can be given in terms of frequency as h nu. This energy can be given in terms of wavelength, hc by lambda. Okay, similarly the threshold energy or the work function can be written as h nu naught. It can also be written as hc by lambda naught. K max can be written as, or maximum kinetic energy can be written as half of mv maximum square or ev naught. Okay, that we got in the previous discussion. Now m is the mass of the electrons, the photoelectrons. Okay, so that is about Einstein's photoelectric effect or Einstein's photoelectric equation. Now from here we have certain discussions which I will try to do a bit briefly. Okay, I'll show you a relation, the V naught versus frequency relation. Okay, and the graph V naught versus frequency. This can also be done as V naught versus 1 by lambda. Now to get this, we will have the above equation, E equals to phi naught plus K. We are writing down K only, not K max now. So since it is V naught versus nu, energy can be written as h nu. You have phi naught plus kinetic energy can be written as EV naught. Okay, now EV naught equals to h nu minus phi naught, and V naught equals to h by E nu minus phi naught by E. Now those of you have done coordinate geometry in class 11, you know equation of a straight line, right? So if you compare this with y equals to mx plus c, which is the equation of a straight line, you get slope m equals to, that is the inclination, slope means inclination, m equals to tan theta equals to h by E. H is Planck constant, E is charge of an electron or a proton, right? So both of these are constant, therefore m is constant for all metals. Okay, the slope is always a constant. But look at the intercept value is minus phi naught by E. So phi naught will vary from metal to metal, therefore the intercept varies from metal to metal. Okay, whereas E is constant here. Now if you plot a graph between these two, like V naught versus nu or V naught versus frequency, the graph comes out to be like this. So this is the slope theta, this is nu or 1 by lambda. You can do it as 1 by lambda also, you can check the PDF. I worked it there, and this is V naught. Okay, so this is the graphical study. Now, factors affecting photoelectric current. Factors affecting photoelectric current, I am writing there as I. Number A, effect of intensity. So this will be a very brief session. I won't go into the elaboration of this. So we discussed that intensity is directly proportional to photoelectric current. L is directly proportional to I, and therefore the graph between L and I was this. L versus I. It's a straight line. Factor number B, there it was effect of frequency. Effect of frequency of incident light, which is nu. We came across that frequency directly affects maximum kinetic energy. It affects your speed, maximum speed squared, and it affects stopping potential. So effect of frequency on photoelectric current is the question. Therefore nu do not affect I. Nu do not, frequency of incident light do not affect the magnitude of photoelectric current. Okay, that is factor number B. Number C, effect of potential. Effect of potential is number C, and number D is effect of frequency on stopping potential. Well, I'll combine these two discussions together, because if I have to elaborate this, there's a lot of talk I have to do. But considering this as a recapitulation lecture, I'll brief. So this is like one graph. We'll do a comparative study. And this is the other graph. All right. So one thing you have to note, when the graph merge on the left side, okay, this, then frequency along with the stopping potential along with maximum kinetic energy of the 4 electrons, they will be constant. But when the graphs separate on the left side, then frequency will be variable, stopping potential will be variable, even kinetic energy of the 4 electrons will be variable. On the right, if the graphs separate, then intensity and currents, saturation currents, they are variable. On the right, if the graphs merge at a point, then intensity as well as current is constant. Okay, so I'm just very briefly I have talked about this. Anybody requires elaboration, you can like write to me or you can call me. Okay, so laws of photoelectric effect and photocell, these two topics I'm leaving it on you. I'm moving to De Broglie's hypothesis. De Broglie's hypothesis. So De Broglie proposed that if light can being if light being a wave can behave as a particle, then material particles such as electrons, protons, neutrons, atoms, molecules, okay, they can also behave as wave. They being as particle, they can behave as wave, whose wavelength can be measured by the relation lambda equals to h by mv equals to h by P, where P is the momentum of this material particle, of this particular material particle, m is its mass, and v is the speed, h is the Planck constant. Okay, so we came across a couple of relations, like this was the relation between wavelength and momentum. Then we have a relation between wavelength and kinetic energy, like h by root over twice mk, right? So here k is the kinetic energy. Then we have a relation between wavelength, de Broglie wavelength, and accelerating potential. So there was square root of twice mqv. Then relation between wavelength, de Broglie wavelength, and temperature. Okay, square root of thrice mkt. Now this k is actually Boltzmann constant, kb. What is the value? Boltzmann constant 1.38 into 10 to the power minus 23 jk inverse. Okay, so this is the last relation. All right, so after this we have relation for de Broglie wavelength of an electron at potential V. I gave you as homework, this was given as homework, so the relation comes out to be 12.27 divided by square root of V angstrom. The relation for wavelength of alpha particle, that is 0.101 angstrom divided by square root of V. You have to remember this relation for numericals. Okay, finally we have Davison-Germer experiment. So the experiment has been taken off, actually qualitative discussions are to be talked about. So this is an experimental verification. Experimental verification of de Broglie's hypothesis. So here you have to remember the desired experimental results were obtained at a scattering angle theta equal to 60 degree and accelerating potential 54 volt. Okay, by applying this value, the de Broglie wavelength of an electron was calculated or experimentally found out to be 1.67 angstrom, which agrees with the experimental value lambda equal to 1.65 angstrom. This was determined in another experiment, which comes under Bragg's diffraction experiment, okay, which is known as Bragg's diffraction experiment. However, that is not there in your syllabus. You have to remember this information only from this Davison-Germer experiment. Okay, so I'll close here. From next class onwards, we'll start a new topic. And of course, if you have any doubts, you can write to me. Thank you.